Okay, we continue. In this part, we are going to have a look of the AMD MI300A, this APU product. This APU product is announced December 2023. Again, there is a very important evolution. So I have the same question. Is the GPU not anymore a PCIe equipment? Is that a coprocessor to the CPU? These are the questions because I have to put two question marks here. These are the questions. We are going to find out the answer. If you look at this artistic photo of this MI300A, you can see that we have 1, 2, 3, 4, 5. We have 6 XCDs. XCDs are the accelerator complex dies. And we have 1, 2, 3. Sorry, I need to change the color. We need to change the color. Okay, so we have 1, 2, 3 CCDs, and here you have 1, 2, 3, 4, 5, 6 XCDs. Okay, the CCDs means compute complex die. That's the CPU, and then you have also the I/O die on the chip. I cannot distinguish the I/O die. I think pretty much is in the top, on the top and the bottom. But really, I'm sorry, I don't know where is nice I/O die. But for sure you have an I/O die because AMD has been doing this kind of chip line design for many time. At the same time, you have this HBM memories. This is the HBM memory, another HBM memory, and another HBM memory, another one. You have HBM memories. HBM memories. Okay, so you have these memories. Now, this is the logical view of this APU without the memory. So we have the SCD 01, 02, 03, 04, 05, 06, and then you have the CCD 1, 2, 3. You have these compute dies and accelerator complex dies. These are the computing power. Where comes this computing power? And here another zoom in of this XCD has been shown here. It has been shown a little bit differently than the others because here you have 39, you have 40. Here you have totally 40 CUs. You have 40 CUs. And then you have these ACEs, this AC 0, 1, 2, 3. Okay, that's an XCD. Basically, XCD, this is the XCD, the compute time. We can simply say this is the GPU. Okay, this is simply the GPU. And each GPU has its own level 2 cache. Okay, the GPU is connected to the level 2 cache by this green link, which is L2 to XCD link. And there is the bandwidth for this one. And then there is another yellow line, which is LLC, is last level cache to XCD link. So the last level cache is also the MD infinity cache. This is the last level cache for GPU, and it is connected to the GPU by the yellow line. It is 17.2 terabytes per second. And then there is a drawing line. The drawing line is the link between this last level cache and the memory, the HBM memory. Now, I think there is an arrow here. Red line is LLC to HBM bandwidth, not to XCD. So it's to HBM bandwidth. Okay, so this is the the architecture of the memory. It shows pretty much the architecture of the memory system. Now here in this picture, we can see that the XCDs, the CCDs, and it's layered one by the other. So it's a kind of a 3D packaging. I mean, this APU is really a piece of work. If you look at this packaging, it's quite complex. There are papers describe the packaging of this APU. But for me, for us, it's not our main interest. Our main interest is how it works. That's programmer's point of view, how it works, and how to program this one. And here, let's have a look at this from the AMD document. Basically, this document is saying the greatest generational change in the AMD CDA3 architecture lie in the memory hierarchy. No, the memory hierarchy outside of the compute units. Now, basically, this is saying that the memory hierarchy has been entirely re-architected to take full advantage of the heterogeneous chiplets and to enable cache coherency for co-packaged CPU chiplets in APU products. Okay. Yeah, we are going to dive into this one a little bit because here really this is the key part. Okay. Okay, you have this XCD, you have, I mean, for this GPU, you have the L1 layer cache inside the die with the GPU. And then you have this L2 cache. And then there is also this AMD Infinity cache. So the role of the L2 cache has fundamentally changed with the addition of the AMD Infinity cache. Now, this cache is connected to this is connected by this Infinity network, Infinity fabric. I mean, if you think about that, in the past up to now, the cache has always been attached to the compute die. That's to say that the cache is always connected to the GPU die. It's always connected to the CCD die, and then we have these links between the GPUs, which is going to connect the CCUs, CCDs, the CPU and the GPUs, but the cache has always been attached to the CPU or to the GPU. For this particular product, is in the part it has always been connected to the CCD and the XCD. It has never been put in the other side of the network. But this one, it has been changed because the Infinity cache has been attached not to the CCD and to the XCD. It has been attached to the Infinity cache. Now, which is the last level cache located on the I/O die. So the cache, the last level cache has been put a little bit far away from the XCD and the CCD. This is something new. In the past, the cache has always been put close to the CPU, to the CCD and XCD core. Okay. Okay. So this is something new. We need to continue and have a look at this one. So let's continue. Okay. Now, right now with this kind of memory arrangement. Okay. if you look at, if we come back here, because here, after the last level cache, the AMD Infinity cache, after this last level cache, and then you can reach this memory, the HBM memory. You can reach this HBM memory. But that's normal that the memory is connected to the last level cache and connected to the XCD and the CCD. Okay. Now with this kind of memory arrangement, it's getting more interesting because if you remember for Nvidia and for AMD, when the GPUs, when the Nvidia GPUs are connected, and also the AMD GPUs. Now we take the example AMD MI250. Let's see the Nvidia, the Hopper GPU. Okay, when the GPUs are connected to the CPU, mainly to the x86 CPU by using the PCIe, basically you have two kinds of memory: the GPU memory, which is pretty much HBM, and the CPU memory, which is DDR. And you know, in the era that the GPUs are connected to the host by using the PCIe, or I have mentioned in section 3 that GPU cannot access the CPU memory. This is not okay. But the CPU can access the GPU memory. This is okay. But the other way is not okay. Now, for sure, the CPU and the GPU, they can access their own memory. This is the memory access. But with this AMD APU, the MI300A, what we have is that there is the unified memory, because this SGM memory is connected. There is also a layer which is called this one. This is a layer. This is the last level cache layer. So the HBM memory and the last level cache, and then this is the Infinity Fabric. This is the Infinity Fabric links. And then you have for this, and this is the CPU. You have the CPU connected to the Infinity link. You have the GPU connected to the Infinity link. This is the CPU. This is the GPU. You have them connected to the Infinity link, and you have the last level cache, which is called the Infinity Infinity cache, AMD Infinity cache, and then you have this unified memory. So here for this AMD APU, there's no difference between the CPU memory and the GPU memory, and it doesn't exist anymore. I mean, the CPU memory in the form factor of DDR DIMMs, it doesn't exist anymore. So all the CPU and the GPUs, they are going to share the same unified HBM memory. This is for the APU stuff. It's like that. Okay, so in the Instinct MI300A APU, the HBM memory is unified and shared between the CPU and the GPU. Okay, dramatically reducing the latency and improving communication throughputs. Okay, now this is a very important evolution of the memory architecture, because right now the life of the program will be much more simplified. Their program is going to be easier to handle, and more than that, we need to have a look at this one, because here is getting more interesting. Is that if you still remember, when we have to work with the GPUs connected to the host by the PCIe, we have to allocate variable. We have to allocate a piece of memory from the GPU, you have to use the heap malloc or the CUDA malloc. The heap malloc or the CUDA malloc. These are the function calls you have to call to allocate a piece of memory from the GPU memory. So it's for these are allocate memory from this one, and for the system to allocate a piece of memory from the host, you just use malloc. Okay. And then you are going to have your memory. So you have these two kinds of memory allocation functional calls. They are different, and it depends on where the memory you want to use. You have to use different functional calls. But with this unified memory, all allocation controlled by the OS. So that if you look at this one, this correct GPU, if you call this malloc, heap malloc or CUDA malloc, you have to allocate a piece of memory on the GPU, and this has to be managed by the GPU. It's the GPU who is going to manage this piece of memory allocation. But for this APU, things has been simplified. All allocations controlled by the operating system. All allocations controlled by the operating system. Accelerator driver, GPU driver, is a client of the OS memory management. Okay, so what we can see up to now is that MI300A, it has dramatically modified the memory subsystem. Its memory is the MI300's memory subsystem has been dramatically simplified compared with the traditional discrete GPU solution. So discrete GPU solution, you have this GPU memory, you have the CPU memory, you have two kinds of memories. Each GPU has to manage the GPU's memory, CPU has to manage the CPU's memory, and for the programmers, you have the GPU cannot access the CPU memory, and for there are some workloads for the programmers when they have to work with this kind of GPUs, when they have to work with the GPU memories. But now with this MI300A, there is only one unified memory, and it is measured by the operating system, is managed by the operating system, and the GPU is saying GPU is a client of the operating system memory manager. So the memory subsystem has been simplified. It has been dramatically simplified. Okay. The memory system has been simplified, and the last level cache has been moved close to the CPU and to the GPU to more closer to the memory. So these are the new evolutions. Okay. We need to have a look of what's the meaning of this kind of evolutions. What was the meaning for the programmers? Okay. Before we have a look of this the benefits for the programmers, we need to have this. We need to have a look at this logical architecture, logical block diagram of the MI300A to better understand this architectural evolution. Okay, so you have this MI300A APU, and on the chip, you have 60 chiplets. You have 3 chiplets, CCD chiplets, and you have 6 XCD chiplets. Okay, and each chiplet you have 40 CUs, but because of the production, 2 CUs will be kept to keep the higher production rate. I mean, sometimes some CPU after it has been produced, some CPU won't work. You have to reserve some more to replace the one that won't work, that fails to function correctly. So you have physically 40 CUs, but for the customer, for the user, what you are going to see, you are going to see 38 CUs, okay, compute units. Okay, that's fine. As I said, there is the L2 cache attached to this chiplet. This chiplet, it has the L2 cache. And for the CCD chiplet, okay, you have let's see, you have it seems it has 8 cores. It has each chiplet it has its own L3 cache. So L3 cache is close to chiplet. And then we have this infinity cache. Infinity cache is also called this last level cache. Okay, so for the CCD chiplet, this is the L4 cache. For the XCD chiplet, this is the L3 cache. So, but it's called the last level cache. And then beneath this last level cache, you are going to have these memories. You have the HBM memories. But the fact is that the 6 XCDs and 3 CCDs, they are all connected. They are all connected to the Infinity Fabric link. This is the Infinity Fabric. This Infinity Fabric is pretty much on the I/O die, but this is the interconnection network for all the XCDs, for all the CCDs, and for all the Infinity cache. Okay. Each XCD will be connected to the Infinity Fabric. So this is, you have the arrow here is showing this is connected to the Infinity Fabric, and then you also have this this flash which is showing that the CCD is also connected to the Infinity. And at the same time, we have this arrow, all these arrows which are showing that the Infinity Fabric, the Infinity cache is also connected to the Infinity Fabric, like this. Okay, this is a chiplet design. You have the chiplet for the CCD, chiplet for the XCD. You have HBM memory as another. It's not a chiplet, it's another piece of component. You have this Infinity cache, which is on the I/O chiplet. So, and then the Infinity Fabric is also on the I/O die, on the I/O chiplet, and then for this MI300A to be connected to the other systems and also connected to other nodes, what you have is that you have 4 Infinity Fabric links, and you also have 4 Infinity Fabric links, or PCIe links, to be used to connect to the other components of the system. So this is the logical architecture of the MI300A. What I want to point out is that there is a key difference here. The key difference is that the GPU is no more a PCIe equipment. If you remember in the previous part, we have said at the end, we have drawn the conclusion that with this super chip, the Grace Opera or the Grace Blackwell super chip from Nvidia, even though the C2C link has been deployed between the Grace and Opera, between the Grace and the Blackwell, we have the cache coherency between the Grace and the Opera. We have this kind of link, very fast link and cache coherency between the grid and the Hopper. At the end, my conclusion is that Hopper or Blackwell is still a PCIe equipment, is a peripheral equipment connected to the system, to the ARM system. Okay, so that's its status. Is a PCIe component. But if you come back and have a look at this MI300A, GPU is no more PCIe equipment connected to the system. GPU, okay, GPU is no more a PCIe equipment connected to the system by the PCIe links. So it's no more like that. The GPU is no more a PCIe equipment connected to the system by the PCIe link or by the PCIe link, like Nvidia with the enhancements. What I mean is that with this kind of cache coherency enhancement and with this kind of PCIe links with the extended ATS service, that's for Nvidia GPU, is an PCIe component. But for MI300A, the thing has been changed. GPU is no more a PCIe equipment. GPU has been put in the center of the MI300 APU. It has the same status as the CCD. So basically, this one, we can understand that XCD, the GPU, is really a coprocessor to the CCD. Is really a coprocessor because it has the same status as the CCD. This is the key difference. And this is a very, very important evolution. Maybe we can claim this is a kind of revolution. Even if it's not a revolution, it's a very, very important technical evolution because essentially the key point is that the GPU has been brought into the center of the system. It has the same status as the CCD because it shares the same cache as the CCD. It shares the same memory as the CCD and is connected to the system by using this infinity fabric, which is kind of a CPU to CPU or CPU to CPU to GPU or GPU to GPU links. So it's a kind of links between the processing units. So this is the all this shows to us that this kind of GPU has been brought to the center of this system. It has the same status as the CCD. So this is the key evolution. It's very, very, very important. Okay, let's have a look at what's the benefits for the programmers. Okay, if you are doing only computing with CPU, if you have to work with some data in the host memory, this is called in host, in underscore h. H means host. You have this one in the host, so you have a function has to work with this variable, and you are going to have some output with this variable. Both this in and out variable will be with the host memory, and you can just work like this one. Your program will be look like this one. You work on this. You prepare the data, and you call the function to work on this data and give you the output. And the output later on, you can have another for loop to loop over this outlook variable, because all is in underscore h and out underscore h variables are in the host memory. So the CPU can work with this one. But when we have the GPU connected to the host by using this PCIe link, things are getting complicated because here the GPU memory, the green one, is discrete with this host memory. So it's separated, it's physically separated. And the GPU cannot access the CPU memory. So how to make it work? To make it work, you have to have this. You have to you have this data in the host memory, the in edge and the out edge are in host memory, but the GPU cannot access the host memory. The GPU cannot work on these two variables to make it work. What you have to do is that you have to do this heap copy the data from the CPU to the GPU. But before you can copy the data, you have to declare another variable, which is called in device. In underscore D means on the device, on the GPU, and out on the device, on the GPU. And then you have to declare these two pieces of memories for the variable in underscore D and out underscore D, and then you have to copy the data, which is the yellow line of code. The green is you have to declare this variable. Okay, and then because you have copied the data from the host to the GPU, and right now you can work with this in underscore D and out underscore D, because right now they are in the GPU memory, and the GPU can access its own memory. So this GPU functional call can work on this in underscore D and out underscore D. Okay, but afterwards, after the job has been done, this heap memory call, you have to heap memory copy call. You have to copy the output, which is useful to you. You have to copy this data from the GPU to the CPU, to the host. So this is the functional call that you have to copy the data from the CPU to the GPU, and then you can continue. But with this APU design, with the unified memory, right now you don't have the difference between the host and the GPU. Both of them share the same piece of memory, which is called the unified memory. And right now, all this declaration of the variables in the GPU memory, you don't need that anymore. That means the green code, you don't need that anymore. And the yellow code, that means the copy in and the copy out to the GPU and from the GPU, you don't need that anymore. What you can do is that you just call this functional call, and you give this functional call the in and out underscore edge, which means that's the variable located in the host, because you have only the host. You don't have the concept of the GPU anymore. And then you can just pass these two variables to the functional call, to the kernel functional call, to make it work. So this makes things easier for the programmer. Right now, they don't need to care about the discrete memory of the host and the GPU. You don't need to care about, you have to declare a variable in the GPU memory, and you have to copy in and copy out the data. The life of the programmer has been made easier because of this kind of unified memory. Okay, this kind of unified memory. Okay, so this is another piece of code. For this piece of code, that's the same story. You have this. You have to declare these variables in the GPU memory, and you have to allocate the memory for these two variables. And afterwards, you have to copy in the data from the host to the GPU. And after the job has been done, you have to copy the data back, and you have to free this GPU memory. So that's all the workloads for the programmers. with this APU, right now, all these lines of code, you don't need that anymore. So you can just pass this variable located in the host, the X and Y to the functional call, and it is going to work. And you don't need to take the memory copy out from the GPU and to the host, and then you don't need to care about to free these memories you have allocated for this X and Y in the GPU. So we had a look of this MI300A. We know that there is a very important technical evolution, if it's not a revolution, is that the GPU has been brought into the center of the APU chip. It has the same status as the CCD. So it's no more a PCIe equipment connected to the host by using the PCIe link. It's really a coprocessor to the CPU. So this is the most important architectural evolution from the AMD side, and it's a kind of a revolution. If it's not, it's still a very important technical evolution. So we are going to stop here regarding this MI300A APU discussion for this part. So we are going to have a rest of 5 minutes, and afterwards we are going to continue the discussion. We are going to compare this super chip and the MI300A the APU solution, and we are going to continue to have a look of the another solution, which is MI250X, which is very similar to the MI300A. So let's have a rest of 5 minutes.